me really was a very important class, and I hope I learned something out of all of it. So eventually we use his blenders and his stuff to prove some theorems, but well, that's a different history. So, okay, let me just go to the talk, to the mathematics. So the title is essentially the theorem I'm supposed to show. So this is joint work with Adam Kanigowski and Dima Dolgopiat. And before I state fully the theorem, I should explain what do I want to mean with exponential mixing and what do I want to mean with Bernoulli. So Bernoulli will be the very standard notion of Bernoulli. Exponential mixing is essentially very standard, but one have to be a little bit specific on what it is. Okay, so let me define exponential mixing. So we have a smooth dynamical system, infinity diffio. Could be less regularity, but let me just stick with this very simple case. We have M is volume, coming from some volume form. M, we will assume, is compact, even though, again, everything is about some Banach space after all, so you can cook up things if you want to go to non-compact. And then we say that F is exponential mixing if there exists lambda less than 1, are finite, and here is really the important subtlety, is the finiteness here, such that for any phi and psi, CR integral of psi dm being 0, we have that the exists a constant such that this integral dm equals CR times lambda. I think that's correct. Is this readable? Good. Thanks. So, so that's the definition of exponential mixing I want to put. And let me make two comments here. So one is this finiteness of the R. So one could define it so that this happens for every pair of C-infinity functions, but then C-infinity is not a Banach space. And this makes it very bad for the consequences. So maybe it is okay, but I don't know. Neither I know examples of guys that would be C-infinity exponential mixing and not CR exponential mixing, but that's what it is. Second is that I'm not assuming here that M is invariant for this definition. So the volume may not be invariant for this definition, even though for the main theorem, the volume will be invariant, but this will come later. Third comment is that as soon as you have one R finite, then the same is true for any R between 0 and infinity. So you will have a constant that will depend on this R, and then the lambda may change. Of course, by increasing the R, you will still get it. So the fun game comes when you try to push R to 0, and you can reach any positive R essentially having this. Or once you have for Lipschitz function, say you also have for Hurdle function. You have it for C38 functions, you will have it for C1 functions. It's just some easy interpolation.
So you're saying that you allow lambda is independent of R?
No, lambda depends on R.
Lambda depends on R. Okay.
Yeah, lambda will depend on R. So yeah, if you want to apply it for very small Hölder exponent, then the lambda will suffer a lot and will get very close to 1. And well, how this depends, that I don't know. So that probably is interesting. But for us, essentially, what will be interesting is mostly the case R equals to 1 Lipschitz functions, and even more, one can deduce, when doing some approximation, some sort of exponential decay for balls, which is what is important for us. The point is that the ball has smooth boundary, and once the ball has smooth boundary, can be well approximated by smooth functions in a way that the norm, well, CR end up being the product of the norms. So then the norms can be estimated, and then you get this sort of decay also for balls, which is very useful for the applications. Yeah, that's also one other comment. So you can show essentially that this constant is universal constant times, which depends on R, psi star. So you can show this. And I don't have the product of the integrals because I assume that the integral of psi is 0. So then I don't have to suffer with this other guy. And in particular, I'm not talking anything about the limiting measure, even though you can show that there is a limiting measure when you push Lebesgue or push volume by the dynamics, it will go to some limit. And well, understanding this limit is important. So let me give you a couple of examples which are not just volume preserving systems, which I think are interesting. And actually, what is interesting is there are not that many examples after all. Well, not that I know. And I want to put a couple of problems for whether you can answer it or not. For example, simplest example is the north-south pole map. That's the most trivial example, where you will have that Lebesgue measure goes to delta in this thing in a very exponential manner. And so you have something which satisfies the condition of exponential mixing, even though I'm not sure you want to think of this system as being exponentially mixing. But still, the fixed point is an exponentially mixing system after all. Now, something that for me was somewhat surprising, even though after you see it is an obvious property, is not only the thing has to be hyperbolic, the north also have to be hyperbolically repelling to have the exponential mixing property, because you want to get far from the north at good speed. So this also is telling you something about the repeller. So yeah, maybe there is also one comment I should have said. So the definition I gave is not reversible in time. So you are taking n positive, you are not making the assumption for n negative. So it's something what happened with the future. So it has to do with some sort of dissipativeness of the system, in a sense. So this is the first example. The second example, of course, is pretty much the same, which is axiom A attractor. And then you either focus on the basin of attraction, or you just go and assume there is only one attractor and the rest of the system is axiom A. Now, of course, a lot of systems are inside this business. There are all the examples given by Dolgopiatov and also flows and whatever extensions by groups. So all this theory that will give you mixing systems when you have the full volume. So I'm just mostly giving you examples where the volume is not preserved. But there is one question, which is one more example that should be is the Enon map or an Enon map. Exponential mix. Okay, and there are a theorem, I think there is even a paper which has this as a main subject, the Enon map being exponential mixing, and I'm asking it again because the exponential mixing of the Enon map in general, it's proof with respect to the SRB measure, but I want here the volume, or area in this case, to go exponentially to this SRB measure. And the subtlety appear in a sense similar to what Omri was discussing, but is for a family of points that in principle cannot be detected by these symbolic systems. Because the big problem, if I can do some sort of picture here, is you have an unstable manifold for your Enon guy, and then you will have this spacing set, which is very small here. So it's very tiny. The vertical is the size of the stable manifolds on this spacing set. And then you go to the next level of the spacing set, and these tables are even smaller. And to have some sort of nice exponential mixing, you will need these stables to, in a sense, be large enough to capture a good, nice, open neighborhood of this unstable manifold and to suck it into that tractor. So you cannot do it because this, of course, having good stables everywhere will be some uniform hyperbolicity. So the question is how you are supposed to get the good uniform neighborhood, even though you don't have uniformly long stable manifolds. So there is a paper by Benedict and Viana which show, I think it's Benedict and Viana, we show that the Enon attractor, so the basin has no poles, so the stables do fill fully the basin of attraction, but here you want a quantitative version of it if you want to do something like that. So anyway, so that's a question.
Federico, if you have, there are these examples of coexistence where you have several attractors or you have some sinks and separately, and yes. you're not dealing. So I'm trying to understand the question. You suppose you have one of these things with an SRB measure. Is the question for and the basin is fairly large. Is the question for that, or what happens in the case where you have many of these types of attractors?
You have to concentrate on the basin of attraction. So,
of the measure of the. Okay, thank you.
But in general, it's just one. If I can find one parameter and one example, I will be happy. So.
Sorry, Federico. Enrique wants to.
Okay.
Federico, so this result exponentially in the one-dimensional context, you could replace the volume by Lebesgue.
Yes.
Is it known or is it easy?
I don't know whether it is written, but
everybody frozen.
At least I thought it should follow the Ekman condition that it is true. But I don't know really. I didn't make any computations, and I'm not sure it is written.
No, well, I didn't hear anything because my camera totally froze the whole computer. The question was, I don't know. I was so the question is in the one-dimensional context. We know that there are many parameters where you have a CBR and blah blah blah. No, so this is a large class where Bernoulli mixing, etc. is known that it happened. It's easy to prove that the just exponential and mixing in respect to Lebesgue will imply Bernoulli.
In this case, yes. In this, for the one-dimensional, yes. And also, I think for this Ekman map, at least you should have this exponential mixing. So, but it's not done. So I think yes.
I don't know if the result. Well, yes. So they are total measure in the complement of the hyperbolic, the Ekman. No? So
yeah. Yes.
So in this case, you mean Bernoulli for the natural extension, right? Because the endomorphism situation is very different.
Yes, that's what we would it be. Yes. Yes. I I wanted to say something else. Okay, let me move on this. So, so these are about examples. So the way I came into trying to think on this exponential mixing condition and these exponential mixing problems was in a conference in Pisa, where the people just started to ask, so does exponential mixing imply positive entropy? So that is it known at all? And it seems that no one knew, and even though the answer is reasonably simple, so no one thought before about that. And I started thinking a little bit about that, and in trying to understand what's really the meaning or some sort of geometric meaning of exponential mixing. I hope I can say
so try to prove Bernoulli. You have dynamics or whatever. You have the quadratic map, you have the Enon map, whatever. No? So it's a pain to try to prove Bernoulli for many parameters. And none is still this big deal that you guys were discussing before. But why proving exponentially mixing is going to be cheaper or easier? No, because you have your theorem that exponentially mixing implies Bernoulli.
This is harder. So if you understand the logic as the guy that is in the left implies the guy that is in the right or vice versa, so then it's strictly harder. That's what the theorem says. So Bernoulli is easier than exponential mixing because one implies the other. So yeah, certainly proving exponential mixing is harder than proving Bernoulli. But well, on the other
maybe there's also maybe exponentially mixing could be something that is more checkable numerically, no? Something that could be.
You have this spectral gap theory, so you have this open, and you have to understand a spectrum. And sometimes, for whatever reason, the system comes from some source where you can compute this spectrum, and then you don't need to prove Bernoulli.
Sure. Thank you.
Yeah, sometimes even when you go, say, to group actions, then the group may be large and the group may imply some spectral gap because the group is helping you, and then the individual element of the group will have this exponential mixing property. So just some magic or things like that. But yes, thanks. Okay, so let me define another notion, which is the geometric expansion property, or depending on Ekman property. So depends on how you want to call it. So which is the following. So you have f from m to m, and we say diffio, actually homeo will do. We say f has this guy, geometric expansion property, or Ekman, depending on what you want to call it. If there exists some lambda smaller than 1, let's call it sigma, because it's different from the lambda. Very isolated, such that for every x in M, the infimum actually, I want it even more beautiful, and C positive, the infimum in N positive of the diameter of Fn of the ball of radius lambda to the mx is larger than C. So what this means in the picture is that you take a exponentially small ball, doesn't matter where it is centered, you iterate it n times, and you see something macroscopic. You can actually see any place in your manifold after n iterates, so any exponentially small place, and it macroscopically, it expand in at least one direction, which will make it macroscopical instead of microscopic. So that's this definition, which is very much related with the Collet-Ekman property in one-dimensional dynamics. So it's essentially equivalent to the standard definition of Collet-Ekman in one-dimensional dynamics. And it has a very important implication, which is that if, it's a very simple lemma, that is if F has this property, then for every measure mu, ergodic probability measure, the largest exponent of mu is larger than essentially the minus log of sigma, but some C naught positive. So there exists a C naught such that this is true. And all these
sigma, excuse me, does sigma and lambda have something to do with one another?
Yeah, there is yet another lemma. So let me say that if you have F is exponential mixing, then either Fn star Lebesgue goes to delta at a fixed point, or you have this geometric expansion property. And once I put this lemma, what you get is the lambda from exponential mixing determines a sigma modulo some dimensional constants. So you can compute it explicitly, one from the other, and the sigma can imply the C naught modulo some dimensional quantities again. So you do some computation. So it's just some easy exercises. And the last, so this lemma, so all these definitions and this lemma give you that if you are volume preserving, then exponential mixing implies positive entropy, at least, which give you, it's equivalent in this setting to have one non-zero exponent. And actually, well, we are going to prove more because we are going to prove is Bernoulli, so it's much more than positive entropy, but at least this settles. But of course, you have the examples for these non-zero exponents of the possibility of the measure going to an atom, as we saw in the north-south pole. So that's about the general machinery.
Federico.
I don't say much about this proof of these lemmas, but
Federico,
I hope,
sorry.
yes.
So just a curiosity, how weaker is if you demand that the volume of the board gets macroscopic instead of the diameter?
Well, that would be somewhat different. So you you will not get the volume growing. Well, depends on what's the setting and which X.
Do you think that, for instance, do you think that this lemma that you wrote, the first one, would be true with this changing the definition?
Yeah, well, if the volume gets macroscopic, then the diameter gets macroscopic as well, because you have a bound. So,
of course, yeah.
But it is, when you go to non-invertible systems, then things comes a little bit more complicated into establishing this business, but still I think it should be okay. And then in this case, still just the diameter is good enough to get enough one exponent, but it is true that maybe if you, in this setting of non-invertible, you can actually ask the volume to become large. And then still it's not clear that you get more than one exponent positive. Yeah. So I don't know how to make it to actually, well, you have exponential mixing, a lot of examples of exponential mixing with only one exponent being positive. So yeah, it's not clear that you can use something else to get more exponents positive.
Thank you very much.
Okay, let me then, so I hope I get a little bit more deeper into what would be this consequence of this geometric expansion property. And actually, when they measure that this invariant is volume, you get much nicer than just this geometric expansion property. And yeah, I hope I can explain. Okay, so let me see. Okay, let me give you one example on how you prove exponential mixing for total automorphisms, because this is very easy, very cheap, very simple. Of course, when you have to fill in the details, it may take long, especially if you are like me. But the picture is very simple. So, so what is exponential mixing for a total automorphism? So you have two balls. But it's not this cubic balls, but not only cubic balls, they are they have axes which are parallel to the invariant axis of your dynamics. Okay, so that makes your life much simpler. Then what you are looking is to f minus n of one ball intersected with the other ball, and you want to compute this measure, and you want to compare it with this product measure. Okay, so that's pretty much what you want to do, and you want this to decay exponential in n modulo some constants that will depend on the size of the balls. And actually, it will be interesting that the constants are good enough so that you have some good estimates on the radius. So you can really estimate differently the radius and the n have separate. But anyway, so you want to estimate that. So how you do this? Well, you go here. This guy has some size A and some size B. Now the vertical size B is here going to be the unstable direction. So let's call it U actually. It should be nicer. This is the U direction, the red direction, and then I take this ball one. Here volume is invariant, so going forward or backward is the same. So let me simplify my picture and go forward here with the n. And then when I take this Fn of this ball, what I get is the following. I get a very long guy. So this red becomes very, very long. So we go here, here, here. So it really gets extremely long. And how long does it get? Well, I iterated n. It gets lambda to the n times u long. Okay, but it does not only get lambda to the n times u long, it also, since this direction is a linear direction on the torus, and I'm assuming some nicety of it, so that it is dense, this unstable direction, it becomes not just dense, it becomes equidistributed, and it becomes equidistributed at a good rate. So it becomes 1 over lambda n times u to some alpha equidistributed.
Federico.
Yes.
Please write in a black pen, otherwise we cannot see.
Good. Thanks, Ceci. Lambda u long is 1 over lambda n u to the alpha equidistributed. Okay, so what does it mean? It means exactly what is in the picture. So I have this other ball, which I'm assuming its radius is much larger than what is written here. So it's some fixed radius delta, which when n is large enough, this will be much larger than this. And then the measure of this intersection, so these lines intersecting here and with this ball will be comparable to the measure of the ball. So that's exactly what you get. On the other hand, this is this unstable line, this, then the other side, if you assume it's stable, or even if you don't assume it's stable, you just assume it's center stable and it's all negative in the other, or less than or equal to 0 in the other direction, they just stay here and enlarge a little bit this. And when you look at the measure of the intersection here, what you are getting is on the u direction, you are getting the corresponding equidistribution. So you're getting the right measure of the horizontal here, essentially, times the measure of the other direction coming from here. So this is this product here. So what I want to emphasize then is that where does this exponential mixing come from? It comes from the polynomial equidistribution of the unstable foliation. So all this picture was just to say that the unstable foliation is polynomially equidistributed. And this is the same as exponential mixing. And actually, that's how you can prove exponential mixing for geodesic flows and for total automorphisms and for a lot of systems.
So what you say, is the polynomial equidistribution is not the same, it's implied exponential mixing.
But you can show it is, what I just showed is how polynomial equidistribution implies exponential mixing. Now, what is also true is that exponential mixing implies the polynomial equidistribution. And that's what I wanted actually to point out, because in a general framework, there is not even unstable foliation. So we can prove there are positive exponents, so you have Pessin theory, there are unstable manifolds. But this manifold, they define a foliation in a sense, in a Pessin sense, which is a very weak sense. And from this very weak sense to talk about polynomial equidistribution is very hard. And yet, saying exponential mixing is very easy. As we saw, I define it very easily, and has the same implication. You have this sort of polynomial equidistributions of unstable, which is a picture pretty much like the one I draw. And this is the very basis of the showing of Bernoulli.
Okay, but so you are going to show first that exponential and mixing allows you to have positive exponent and then produce those unstable manifolds.
Exactly.
For almost every point, but the way that they will distribute is as it happened in the Anosov case.
Exactly.
Okay.
Federico, the foliations, you cannot expect them to be CR.
No, just there is one leaf. So it's
just one leaf. Just one leaf.
That's the show.
Just one leaf.
So you put the leaf-wide measure and you look at how on a very large unstable of radius r, and so you take unstable of radius r is supposed to be very big now, centered in some point x, and this you want to be 1 over r to the alpha equidistributed, whatever it means.
So in particular, the exponential mixing gives you large Pessin manifolds.
Yes, in particular, it will give you large. Again, everything now I'm talking is volume preserved. So in this whiteboard is volume preserved. So the exponential mixing will give you exactly not just very large unstable manifold, even though this may not be, I wrote it here in the nice automorphisms is a disk, so to speak, in the typical dynamics or abstract dynamics, it may be just a very thin strip along a stronger one-dimensional. I don't know really what it is. But what is true is that the unstable measure on here becomes equidistributed. So it has this property that the measure of not just now intersection of ball, if I take this iteration of an unstable of some size here, epsilon at the point x, I intersect it with the ball, I look at the unstable measure of this, and this will look like the unstable measure of the original. And
sorry, Federico, I have a comment. In the polynomial equidistribution of the unstable manifolds, you fix R and you get the alpha, or this is for what?
It's the same alpha for every R. There is a lot of quantifier. And actually, when you get into the actual statement, the amount of quantifiers is really beyond my understanding, essentially. So,
okay.
So you have epsilons here, X, and
okay, but you have the R and the alpha for every X.
Yes. Essentially, the alpha, you can read the alpha from rate of expansion of an unstable versus exponential mixing property.
Okay, thank you.
The alpha will come.
Federico, sorry, just another curiosity. With this argument that you explained for the linear case, the conservative linear case, if you have a two-dimensional unstable manifold that splits in two subbundles, the rate of mixing that you obtain would be the strong unstable or the weak unstable one?
Well, it's actually a mixture of both. So you can get a rate of mixing from the strong unstable already as soon as the strong unstable get distributed, and you will get this rate of mixing. And this is very important. There is a work of Spazier and Gorodnik and Spazier, where they prove that, and they show that the rate of mixing only depends on the fastest as soon as this fastest is distributed. And this is very helpful when you try to get the same rate for different automorphisms. But now you have the second direction, and this goes into your help because then you have some better disk and some better bounds. And now what exactly the rate of mixing is, that I honestly, I should think about it. I guess the Jacobian, so the product of the eigenvalues should be related somehow, but I'm not quite sure. So I didn't sort that much.
Okay.
Federico, are you saying that as soon as you have a Pearson set in measure preserving, you have some alpha?
If you have this exponential mixing, then the
a priori, what is the hypothesis?
Exponential mixing.
Oh, exponential mixing is
yes, for volume. Yes. Yeah. No. If not, you don't get them.
Okay.
But again, what I wanted to express is that this alpha here and the exponential mixing are very intimate properties. So if you have different rate of mixing, for instance, you have some polynomial rate of mixing or something intermediate, this will affect the sort of distribution you get for this unstable foliation. And then there is a game one can play about rate of mixing, how much equidistributed is unstable, and eventually what is the expansion along the center direction. Okay, so I need to move on. Okay, so that's how we relate exponential mixing to equidistribution of unstable manifolds. Now comes the next level, which is how you prove a system is Bernoulli. And this brings us to Ornstein-Weiss, which also goes back to Ornstein himself. And there are 3 levels of Bernoulliness, which has a lot of implication for people that study Bernoulli systems and partitions and all these abstract ergodic properties. So it's Bernoulli, weak Bernoulli, and very weak Bernoulli. So, so this is something you said about the partition and the dynamics, not just about the dynamics. So you give the dynamics, you give a partition, and then you can call this partition Bernoulli or weak Bernoulli or very good Bernoulli, depending whether it satisfies this or that property. Now, when you look only at the dynamics and forget for a second about the partition, and you want to ask whether the system is measurably isomorphic to a Bernoulli system, then the three notions are equivalent. So if you have a partition that is Bernoulli, if and only if you have a partition that is weak Bernoulli or very good Bernoulli, and if and only if your system is measurably isomorphic to Bernoulli. Now, as an example, the standard Markov partition for a total automorphism is not Bernoulli. Okay, because for a partition to be Bernoulli, you have to look like the rectangles of a Bernoulli sheaf, which means that there is no transition matrix, or the transition matrix is all ones. So everyone intersects to everyone, and with the measure of the intersection of cylinders is exactly the same as the product of the measure of the cylinders, so it's complete independence. What is weak Bernoulli then? Well, weak Bernoulli is exactly what you get from a Markov partition. So you get that the measure of the, actually you can think slightly different. Let me now just switch a little bit what I said. And it means that the measure on a rectangle is roughly the product of the measure of the stable measure and the unstable measure. So that's essentially with Bernoulli, and the roughly means there is a Radon-Nikodym derivative, and this Radon-Nikodym derivative is nice enough so that when you look in a very narrow rectangle, say in the stable direction, then this Radon-Nikodym derivative is almost one, which is reasonable because any measure of function is almost continuous, which is almost constant. So that's that is what is with Bernoulli. So is this property that the measure of this very thin rectangle here is essentially the measure of this times the measure of this, and essentially no Radon-Nikodym derivative, which is very good. Now, what is very good Bernoulli? Very good Bernoulli is a little bit simpler. So let me then go back to Bernoulli to explain what is very good Bernoulli. So,
Fede,
yes.
So you were saying, sorry, no, it's pretty good what you, all the stuff that you're saying. So you were saying, for instance, that the polynomial rate is the way that people use in a way to produce exponential mixing, but Bernoulli, etc. But then use exponential mixing is much more stronger information. And so if you say, you know that it's whether it's hyperbolic or non-uniform hyperbolic, whatever you like, and you cover your boxes with rectangles in some way, given for some type of partition that somebody is going to provide you by some theory. And then you say, okay, so you know that it's exponential mixing, so you have to be covering all the rectangles with this exponential decay. So you are claiming that after that, you can conclude that the way that the foliation is going to be distributed have to be polynomial.
Yes. Exactly.
So basically what you need to do is this idea of really just from scratch, from observable information, which is exponential mixing, to build your hyperbolic, well, non-uniform hyperbolic foliation.
Well, essentially, yes, but of course you have the Pessin theory already settled. So
okay, so you need to prove this, but you need more than just the Pessin theory.
Well, yes, exactly. So you use your observables to show that these unstable that were built by Pessin are doing the same as the observable is telling you to do. And yeah, that's a good part. More than half of the paper is just into settling this problem. Actually, when writing it, we first thought that we could indeed do exactly what you said. So use the less possible Pessin theory and just try to rebuild everything from the observables and things like that. But then we just use Pessin theory. So it is there. And why wouldn't you use it if you have it there? So it really is
pretty cool.
Okay, and yeah, so So let me rephrase what I said here about this with Bernoulli. So I'm taking here this narrow rectangle where the vertical are unstable and the horizontals are stable. So essentially what I said about the measure is essentially equivalent to the following, is that I have the conditional measure along the vertical here, the conditional measure along the vertical here, and I do holonomy between these two guys along stables. And the Radon-Nikodym derivative of this holonomy is 1 or almost 1. And that's pretty much the same as saying that this is sort of a product measure with Radon-Nikodym derivative 1. So then this weak Bernoullicity is nothing but the absolute continuity of the unstable foliation. And the fact that this Jacobian can be taken very close to 1, but that's just because the two guys are very close. Now, what is very weak Bernoulli? So very weak Bernoulli is essentially the same, but the big difference is that now this pairing is not along stables. It's just a pairing. And it's a pairing that will satisfy some dynamical property, which is that the distance of this holonomy map is x into theta x to Fn of theta x. So the amount of n's in the 0 n where you have this divided by n is larger than 1 minus epsilon. So that's what you want. You want this not to be in the same stable manifold or even center stable, because this is local non-expansion, not just contraction. So you don't want them really to not get separated, but you want them most of the time not to get separated from time 0 up to n. That's all you want. Okay, and then there is a lot of quantifiers. So given epsilon, there exists some capital N naught, so that for every n larger than n naught, I can build this theta so that something like that is happening. So, but that's very good Bernoulli. So I don't need to have this full matching along stables. I'm allowed the 2 points here to get separated from time to time as soon as they get close together at the end of the day and for a large proportion of the orbit. So that's very Bernoulli, and that's the typical way of proving Bernoulli is to show in this very weak Bernoulli property. So you need to do this matching. So you need to find this theta. So now how you find this theta? Actually, I did this vertical unstable very small because you can chop and do it in small pieces and then put them together. But actually, you have to do it in as long as you wish. But again, you do it locally and then you patch them together.
Sorry, Federico, the thetas need to have uniform size or?
The theta, no, the theta is just this, and you need theta star, the unstable measure on the left, to be the unstable measure on the right. So you need the theta to be measure preserving. Then, of course, being almost measure preserving is good enough and things like that. But that's all you need. It's just a measurable function from the left unstable to the right unstable that bring the left measure to the right measure, and that most of the time from 0 up to capital N, you do this shot. And this theta depends on N and S.
Okay. Thank you.
Now how you do it. And actually, this is the general way that Adam did it for the total automorphism. So this was done by Ornstein and Weiss for total automorphisms where the center direction is isometric. Then Adam did it without the center direction being isometric, so it will grow polynomial probably. And now this is pretty much the same picture that will happen here. So you take these two unstable. Unstable 1, unstable 2. Okay, now you have this epsilon which is fixed over there, and you want to make sure you have this pairing which is up to size epsilon. Then what you do, you cover your manifold by boxes of size epsilon, all of them, and you will have to disregard a lot of boxes, which again will cover only a small amount of space, and that's good enough for this good value. Now you go to some f delta n, actually set epsilon n, okay, iterates of these two guys. Okay, so of the U1 and of the U2. So the U2 is the blue one, the U1 is the red one, and you consider this guy and this guy. Now this becomes very long, that's the whole business, and that's the consequence of exponential mixing, as not only very long, in each of these balls, these two guys become equidistributed. Just some vertical guys here and some vertical guys here. Okay, at this epsilon n iterate. So these guys here is epsilon n each. Now, in this square, so actually these squares are of size e to the minus some delta n, where delta is reasonably large, but reasonably small as well. So it depends on the center expansion or contraction, which the center is 0 Lyapunov exponent, so you are fine, or maybe negative, so the stables are also there. And then inside here, since I have that both the blue and the rectangle inside here are equidistributed, I have that the Lebesgue measure of the blues and the Lebesgue measure of the reds in these rectangles are the same. So I have a theta map from blue or from red to blue. Blue here. Having in each of these rectangles. This theta will be measure preserving, and it is not just any theta map, it will be a theta map which is a diffeomorphism between the red and the blue, whose Jacobian is very close to 1, so that's why, and it's essentially 1 if you modify it a little bit. And so it has respect the measure, so that's how you get this property here. And also you will have the theta of x belongs to some stable manifold that is good up to size, up to n iterates of this x. And actually it will be 1 minus epsilon n of the iterates here. So for the remaining of the iterate, this guy belongs here. And so since they are very close here, you get that they are E minus delta n close. Then you start iterating 1 minus epsilon n times, and they get separated times some other epsilon naught, which is the center expansion, and you make this still be negative. So the delta is a little bit larger than the epsilon naught, but all the guys are very small in any event. So this is very smaller than 1, and hence I get that from time epsilon n up to time n, they stay together. And that's this property that appeared here.
Sorry, Federico, in your figure, U1 and U2 are, which are unstable foliation or disk?
Two unstable leaves. Two unstable.
Are you assuming that you have unstable foliation, or?
It's just two unstable leaves coming from some pacing set of size 1 minus epsilon.
Okay, just thank you.
And then actually this is not exactly that theta, so I bring now this theta back using the dynamics onto here. And then when I bring it back, so even though here it looks pretty nice, this theta, so it just slides horizontally. So when I bring it back, it will do a mess because it's minus epsilon n iterates of what the picture I had here distributed in several rectangles. So it's really quite a mess what happens with the theta here. But what does it here is reasonably clear. So there is one subtlety, which is the absolute continuity of this center stable foliation. And the whole point is that the center stable foliation is absolutely continuous. So even though typically the center stable foliation should not be absolutely continuous, it is absolutely continuous at this scale, because you just do an easy version of the absolute continuity in an awesome situation, and the size of the Jacobian comes from the distance of the 2 points, and the 2 points are originally e to the minus delta n apart. So this is what really controls the Jacobian and make this Jacobian very close to 1, actually, not just absolutely continuous. So in this way, that's how you build the theta. I think I ran out of time. So yeah, I'm sorry for the mess, but thanks.
Thanks.